Hello students, talk on civil engineering. Let us discuss the most important questions from RCC, the question number 61 to 120. Question number 1 to 160 are included in part 1. The part 1 link will be given in the description. Please go through that video. Let us start the video. The question number 61, the traditional method of design RCC structure is working stress method, and this working stress method is also called as the elastic method, modular ratio method, and factor of safety method. Question number 62, as per IS 456, the partial safety factors used in limit state method for concrete and steel are: for concrete it is 1.5, for steel it is 1.15, whereas for serviceability will be taking 1 as a partial safety factor, and in working stress method for concrete will be taking 3 as a partial safety factor, and for steel 1.78 as a partial safety factor in working stress method. Question number 63, to compute the design load in limit state method, the working load is computed by multiplying 1.5 with dead load and live load. Okay, so that means the partial safety factor for design load is 1.5, and this changes based on the load conditions or load combinations. Simply if we are using dead load and live load, we will be multiplying with 1.5, and dead load with other loads like earthquake or wind loads, then you can simply multiply with 1.5, or else 0.9 of dead load plus 1.5 of earthquake or other loads. And also other combination is also there, that is 1.2 into dead load plus live load plus other loads. Okay, so usually we'll be taking the maximum of these three as the design load. So try to remember these load combinations also and load factors. Let us go to the next question, question number 64. According to IS 456-2000, which one of the following statements about the depth of neutral axis XU balance for a balanced reinforced concrete section is correct? So for a balanced neutral axis, which of the statement is asking to pick the correct statement? But here I have provided directly. I have provided the correct statement. That is, the XU balance depends on the grade of steel. Grade of steel only. Remember. So the balanced neutral axis or else the critical neutral axis will depend on the grade of steel. Okay. So whatever the values provided in IS 456, so those are based on the depth of effective depth and the type of steel or grade of steel, right? For Fe 500 you have one value, for Fe 415 you have different value. We'll see those values also in next probably in next slides. So remember, the balanced neutral axis depends on the effective depth as well as the grade of steel. Question number 65. Concrete and steel reach its ultimate strength at same time in balanced section. So in balanced section, the strain and stresses will reach at same time in steel and concrete. That is our assumption. Question number 66. In RCC structure, most of the practical sections are of under reinforced sections. under reinforced sections. And in under reinforced sections are most recommended, or these are the most recommended ones. And you know that in under reinforced sections, the provided AST provided will be less than the AST, the balanced section AST. And not only that, and the movement generated, or the ultimate movement, will be less than the movement of balanced section movement. Okay, and also neutral axis, actual neutral axis will be less than the balanced neutral axis, or else critical neutral axis or maximum neutral axis. So these values are also important. Sometimes he will ask in the question. Okay, so provided AST or AST will be less than the critical AST or maximum AST. Mu will be less than the maximum movement. XU will be less than the maximum XU max. Okay, and so this is wrong one. So failure will be, you won't have the sudden failure, you will have gradual failure or slow failure will be there. You will have clear warnings. Warnings will be there. So that's the reason these under reinforced sections are recommended. Okay, and here the steel reaches first, and the steel fails first. So try to remember these points also, which will help you in the exam. Question number 67. As per IS 456, for a rectangular section with Fe 415 steel, the maximum neutral axis lies at. So for, as I told, as we have discussed earlier, so for a balanced neutral axis, the depth of neutral axis depends on the grade of or type of steel. So for Fe 415, the neutral axis lies at 0.48 of effective depth. Okay, so I have provided other values also. For Fe 250, it lies at 0.53 of D. So these are the XU values, XU balance values or XU max values. And for Fe 415, 0.48 D. For Fe 500, 0.46 D. Okay, so with the type of grade, or as the grade of steel is increasing, the depth will decreases. Question number 68. The limiting percentage of steel can be computed using 0.36 FCK by 0.87 Fy, XU max by D into 100. Okay, so this is the equation to find out the AST for the balanced section. Okay, why this is important? Because this is important whether you can say, based on this you can say whether this is a under reinforced or over reinforced if only the AST is provided. If AST is less than this value, it is under reinforced. If AST is greater than this value, it is over reinforced. Right? So try to remember this formula. Remembering this formula is very easy. Simply you will have above you will have concrete strength, and below you will have the steel strength, the 0.36 FCK, and below you have 0.87 Fy. And here this is the maximum neutral axis elements, that is XU max by D. And if you want to get this into a percentage, you need to multiply with 100. That's it. 0.36 FCK by 0.87 Fy into XU max by D into 100. Let us see the next question. Question number 69. The actual neutral axis of the given section is calculated using 0.87 Fy into AST divided by 0.36 FCK into B. Okay, so this is the equation to find out the actual neutral axis. Simply you can derive this equation by simply equating the compressive force with tensile force. Okay, This is your tensile force, and this is your compressive force. Question number 70. What is the probability of failure of structure in limit state method? So in limit state method, the probability of failure of structure is 9.75%. 9.7%, or in decimals it is 0.0975. Question number 71. Doubly reinforced beams are recommended if mu, the ultimate moment, is greater than the mu limit or mu max, or the balanced moment, or else the depth is restricted. If the depth of beam is restricted, you'll go for the doubly reinforced section, or the moment generated is greater than the maximum moment, then you'll go for the doubly reinforced section. Okay, so in case if mu is greater than mu limit, it will be a over reinforced section. Okay, since these over reinforced sections are not recommended, so you'll go for the doubly reinforced section, because this over reinforced section gives a sudden failure, whereas under reinforced section will give a gradual failure, or clear indications will be provided in under reinforced section. So this over reinforced gives a sudden failure. That's the reason these are avoided. Question number 72. As per the given section, the strain and stress variation as per limit state method at section XX is, so at section XX, what is the variation of strain and stress? So answer, strain is linear and stress is non-linear. So in limit state method, wherever the section will be, but the assumption, the condition we'll be taking is the strain will be a linear form, whereas the stress diagram will be something like this. Up to the neutral axis, you will have a rectangular and parabolic portion, and below that you will have a straight line, right? So this is a non-linear, this is a non-linear one, and this is the linear one. Okay, so therefore strain is linear and stress is non-linear. Question number 73. The beam is having effective cover of 50 mm and reinforced with 4 bars of 16 mm dia and 8 mm two-legged stirrups. The clear cover of reinforcement is, you know that what is clear cover? The clear cover is the distance between the outer face of the beam to up to the reinforcement. So here this spacing is your clear cover. Okay, so you have to get this clear cover. So he has given the dia of the main bars, that is 16 mm. So half, you have to take a half of this, and the stirrup is 8 mm. So this stirrup is 8 mm. Okay, and what else he has given? Effective cover he has given. So effective cover means it is a distance up to the center of main reinforcement. Up to the center of main reinforcement. So this value he has given, this is 50 mm. So from 50, if you subtract this value, you will get the clear cover. So that is what I have done. Answer, 50 minus 16 by 2 minus 8. So the answer is 34 mm. 34 mm is the clear cover. The strain at level of stress in compression steel in doubly reinforced section is given by 0.0035, 1 minus effective cover by XU. Okay, so this is the strain at the level of stress in compression steel in doubly reinforced sections. Okay, so the answer is 0.0035, 1 minus D dash. So D dash, in the sense, it is the effective cover for the compression reinforcement, for the compressive reinforcement. Okay, Question number 75. The effective width of flange for T beam is calculated using L0 by 6 plus BW plus 6 into DF. So this is for the T beam effective flange width. So here L0 by 6 plus BW is the width of web plus 6 into DF is the depth of flange. Whereas if we asked for the L beams, so for L beams it is half of this. It will be half of this. Okay. So L0 by 2, if you multiply this with half, it will be L0 by 12. So L0 by 12 plus BW plus 6 from half of 6 is 3. So 3 into DF. L0 by 12 plus BW plus 3 into DF for L beams. Question number 76. The span in which shear force is non-zero constant is called as shear span. The answer, shear span. So in the span where the shear force is constant and it is having a non-zero value, so that span is called as shear span. Whereas pure bending is called as where the shear force is 0 and the bending moment is constant. So that span is called as the pure bending. Okay. Question number 77. 90-degree or vertical crack develops at bottom of tension zone is called flexural crack. Okay. So usually this flexural crack will develop at the center or mid span of the beam, at middle of beam. Okay. So at the center, the beam center, you will have a 90-degree crack. So this crack is called flexural crack. And there are another cracks also there, another shear failures also there, that is 45 to 90-degree crack. So this is called flexural shear crack. So this is called flexural shear crack. And 45-degree crack, so this is called web shear or diagonal tension failure. Web shear or diagonal tension failure, which is having a 45-degree crack. And for flexural shear failure, you will be having a crack of 45-degree to 90-degree crack. For flexural crack, you will have 90-degree crack. Question number 78. As per IS 456, the nominal shear stress for beam of varying depth is calculated by Vu plus or minus mu by d tan beta by b into d. Okay, so this is a formula to find out the nominal shear stress for varying depth. Vu plus or minus mu by d tan beta by b into d. Okay, in another way you can remember, in another way also, you know that Vu by bd is the for nominal shear stress, for a nominal shear stress for a constant varying depth beams, right? For or uniform depth beams, right? So for this you need to multiply the moment values plus or minus mu by d tan beta. Okay, so that's it. So like this also you can remember this equation. Okay. So but you need to divide this with BD. Okay. So just for remembering this, I have splitted this, but you have to divide entire equation with BD. Question number 79. Design shear strength of RCC member depends on grade of concrete and percentage of steel. So the design shear strength tau C depends on the grade of concrete and percentage of steel. Based on these two values, IS 456 is provided the tables. Question number 80. If the maximum shear resistance exceeded by nominal shear strength of beam, even after shear reinforcement is provided, it results into diagonal compression failure. So that means if maximum shear stress, that is tau c, if tau v is exceeding the tau c max, the maximum shear resistance, so then it results into a diagonal compression failure. So if this diagonal compression failure is happening, so you have to redesign the beam by increasing the effective depth, or by increasing the dimensions of the beam. You have to redesign it for shear. Question number 81. The minimum shear reinforcement that needs to be provided in beams as per IS 456 is. So this is the equation to find out what is the minimum shear reinforcement, or the spacing for minimum shear reinforcement. So that is 0.87 Fy ASV divided by 0.4 B. 0.87 Fy ASV divided by 0.4 B. So here ASV is the area of stirrup. Okay, area of stirrup. And you have another equation also for providing the shear reinforcement for net shear force or design shear force. So this is the equation for minimum shear reinforcement. Whenever your tau v is greater than the tau c, your tau v is less than tau c value, then you will be providing this shear reinforcement. Okay. Whenever your tau v is greater than the tau c, so for the excess force, whatever the excess force is there, so that is calculated using this equation. VUS is equal to VU minus tau c into BD. Okay. So for this excess shear force or the net shear force, you need to provide the shear reinforcement using this equation, that is 0.87 Fy ASV into D by VUS. 0.87 Fy ASV into D by VUS. Okay, so in this both the equation for in minimum and the for shear reinforcement and for net shear force or for design shear force, the common are 0.87 Fy into ASV is common. Okay, so except here you will get D by VUS, whereas here you will get 0.4 by B in denominator. That's it. Okay, so like that, compare the equations so that you can remember them easily. Question number 82. The spacing of stirrups in beam should not be more than 0.75 D or 300 mm, whichever is the least. Okay, so 0.75 D or 300 mm. The least of these will be the spacing of stirrups in beam, the maximum spacing of stirrups in beam. Whereas for inclined stirrups, the spacing should not be more than effective depth of your beam or 300 mm. Question number 83. Design for torsion provided in IS 456 is based on. Design for torsion provided in IS 456 is based on skew bending theory. Skew bending theory that is given by Su, based on this engineer. So this is the theory that will be used for torsion design. Skew bending theory. Question number 84. The equivalent shear force that needs to be used in design for torsional movement is given by. So for torsional movement, if torsion movement is given, the equivalent shear force that you need to calculate or that you need to find out using the equation given in IS 456, that is VE, the equivalent shear force, equal to VU plus 1.6 TU by B. So here TU is the torsional moment and VU is the shear force or ultimate shear force. Vu plus 1.6 Tu by d, remember. And you need to calculate the equivalent moment also. So for equivalent moment, the equation is mu plus Tu 1 plus capital D by B by 1 plus 1.7. Mu plus Tu into 1 plus D by B divided by 1.7. Okay. So simply for torsion design, we'll be modifying shear force and the moment. Remember this also. As per IS 456, for torsion design, we'll be modifying shear force and moment for the design of the beam. Question number 85. Equivalent moment in torsional design is considered same as the ultimate bending moment if. So when will be the equivalent moment, that is ME, is considered equal to the bending moment or ultimate bending moment? The answer, equivalent shear force is less than or equal to design shear strength of beam. Okay. So whenever this VE is less than the design shear strength, that is, so the equivalent shear stress, let it be tau VE. So when this tau VE is less than the tau C, the design shear strength, so then you can directly take the actual moment as the effective or equivalent moment. Question number 86. What is the IS 456 recommended minimum eccentricity for axially loaded short column? So for axially loaded short columns, IS 456 recommended a minimum eccentricity of L by 500 plus dy by 30, or else if it is in x direction, it will be L by 500 plus dx by 30 or 20 mm or 20 mm. So you have to take the maximum of these two. Okay, either this equation value or 20 mm. So among this, whatever the maximum, that maximum value you have to consider, and this maximum value, try to remember this also, this maximum value should be less than or equal to 0.05 times of the respective dimension of the column. Okay, so if we are using dy here, so it should be less than or equal to 0.05 dy, and if it is using dx here, so it should be less than or equal to 0.05 dx in order to confirm this is a axially loaded short column as per IS 456. Okay, so try to remember this equation and the 20 mm and these values also. Question number 87. In a short column, if helical reinforcement is provided, the load carrying capacity will be increases to 5%. So that means the helical reinforcement columns will have 5% more strength than the lateral tied members. Okay, so that's the reason the PU for helical reinforcement will be equal to 1.05 times of PU of the lateral ties column. Okay, so this is a helical, this is a lateral ties. Question number 88. The minimum and maximum percentage of steel that needs to be maintained in columns as per IS 456 is. So the minimum percentage of steel is 0.8% and the maximum percentage is 6%. So 0.8% and 6% are the minimum and maximum percentage of steels in columns. Question number 89. A column is reinforced with 4 bars of 32 mm dia and 2 bars of 16 mm dia. What should be the minimum dia of lateral tie as per IS 456? So as per IS 456, the minimum lateral tie the minimum lateral tie diameter should not be less than the maximum dia by 4. So here the maximum dia is 32, right? So 32 by 4. So it should not be less than this value, and it should not be more than 16 mm. Okay, it should not be more than 16 mm. So 32 divided by 4 means it will be 8, I think, right? So it will be 8. Okay, so it should not less than this 8 mm, and it should not be more than 16 mm. So that therefore the correct answer is 8 mm. Okay, you should not take the value lesser than 8 mm. Next, question number 90. The spacing of lateral ties should not exceed 300 mm, or least lateral dimension of the given beam, or 16 times of minimum diameter. So since here he has not provided what is the lateral dimension of the column, or what is the minimum diameter of the bar that is used, so that directly the answer will be 300 mm is the answer. Okay, so the spacing of lateral ties should not exceed 300 mm. Okay, in case the lateral dimension and the diameter is provided, so you have to check through these three statements, that 300 mm and least lateral dimension and 16 times of the minimum diameter of longitudinal bars used in the column. Okay, the least of these three will be the maximum spacing of the lateral ties. Question number 91. Interactive curves provided in SP16 are used to solve uniaxial or biaxially loaded short columns. So these interactive curves are used for uniaxially or biaxially loaded columns. Question number 92. The change in the bond stress if HYSD bars are used in tension and compression as per IS 456. So in IS 456 the bond stress values are provided. For that you need to modify those values based on the HYSD bars that are used in respect to whether it is in compression or tension. Okay, so for if HYSD bars are used in tension, so you have to increase the given values by 60%. Similarly, the bond stress value increased by 100% if these HYSD bars are used in compression. Remember, so that means the bond stress values that are provided in IS 456, those are for mild steel. Those are for mild steel. Okay, those are for mild steel in tension. Those are mild steel in tension. The values that are provided in IS 456. Okay, so if HYSD bars are using, those are increased by 60% in tension, and those are increased by 100% in compression. So that means it will be 2 times of tau BD. If HYSD bars are using in compression, that means 100 plus 100, it will be 200, right? So it will be 2, right? So if suppose if the plain bars, that is mild steel bars, are using in compression, so it is increased by 2%. Okay, because the IS 456 is provided the plain bars in tension, so this tension is if this if mild steel bars, if they are used in compression, so it will be increased to 25%. That means 2.5 into tau BD. Okay. Question number 93. If the bond stress developed more than the permissible value, it can be controlled by decreasing dia of bars, increasing number of bars. Sorry. So decreasing dia of bars, increasing number of bars, and increasing the depth of beam. So these are the three ways of limiting the or getting the bond stress under permissible value. Question number 94. The most critical bond that develops in beam is end anchorage bond. End anchorage bond is the most critical bond that develops in the beam. Question number 95. As per IS 456, the development length of a straight bar is calculated using dia into stress in steel divided by 4 times of bond stress. Okay. Stress in steel into dia of bar divided by 4 times of tau BD. Remember like this. So what is the stress in steel? It is 0.87 into Fy. Okay, so that's it. So remember this formula. Question number 96. What is the anchorage value for the bar of 135-degree bend? So for 135-degree bend, the anchorage value is 12 times of dia. 12 times of dia. So how you can remember this anchorage value? For 45-degree bend, you will be having 4 times of dia. For 90-degree bend, you will be having 8 times of dia. So simply it is the increments of 4. So here you have 4 and plus 4 you will get 8, plus 4 you will get 12, plus 4 you will get 16. Okay, and this will be the increment of 45. So 45 plus 45 you will be getting 90 degrees, plus 45 you will be getting 135 degree, and plus 45 you will be getting 180 degree. Okay, so like that, for 135 degree you will be the anchorage value is 12 dia, and for 180 degree the anchorage value is 16 dia. Okay, and as a note, remember this value also, the for HYSD bars, the maximum allowed bend is 135-degree bend. Okay, so you can't provide 180-degree bend for HYSD bars. The bar may get cracked. And the required development length will be equal to the development length of a straight bar minus anchorage value. Development length of straight bar minus anchorage value will gives you the required development length. Question number 97. If center to center distance of a splices is greater than 1.3 times of lap length, then the lap splices are provided as staggered lap splices. Staggered in the sense, if splicing is happened here, so then for the next bar the splicing should be provided at another with some spacing. So this is called stagger. Okay, so the staggered lap spacing is provided if center to center distance of splices is greater than 1.3 times of lap length. Question number 98. As per IS 456, the size of bars that shall be welded but not spliced. So for bars of greater than 36 mm dia. So for bars of greater than 36 mm dia, so those should not be spliced, but they can be welded. So they should be welded. Question number 99. Splices in flexural members shall not be provided at section where bending moment is more than 50% of moment of resistance. So wherever in the section, entire section, wherever the bending moment is more than the 50% of moment of resistance, there you should not provide the splices. And not more than half of the bars shall be spliced at a section. So at a particular section, at any section, not more than half of the bars are spliced. Question number 100. The size of bars shall not be bundled in flexural members. So for the bars of greater than 32 mm dia, for the bars of greater than 32 mm dia, so those should not be bundled. Those should not be bundled. Question number 101. In earthquake prone zones, the minimum bend provided for shear reinforcement is 135-degree bending. So 135-degree bending is the minimum bending that needs to be provided in earthquake prone zones for shear reinforcement. Remember, this is for lateral ties. For lateral ties. Okay. And the anchorage length for anchorage length of shear reinforcement. For shear reinforcement, what are the anchorage values? Initially, we have seen the anchorage values for straight bars, that is the main bars. So here these are for lateral, these are for stirrups. Okay, so for stirrups, if it is a 90-degree bend, so you have the anchorage length is 8 times of dia, and for 135-degree bend, it is 6 times of dia, and for 180-degree, it is 4 times of dia. Okay, so this 135-degree, that is 6 times of dia, needs to be provided in earthquake prone zones. Okay, so that means it looks something like this. So this will be your 135-degree bend. This is your 135-degree bend. Question number 102. The maximum size of main steel bar for slabs is 1/8 of slab thickness. 1/8 of slab thickness. This is how you can decide the thickness or the size of dia of main steel bar in slabs. Okay, 1/8 of slab thickness. 103. Question number 103. The type of footing that is recommended if the property line is too close to the column, that is combined footing. So combined footing is recommended if the property line is too close, or else if the columns are too close, the footings are overlapping, then you will go for the combined footing. And for load bearing walls, usually for load bearing walls, isolated footings are provided. Isolated footing are provided for load bearing walls. Question number 104. In the design of footing, the soil pressure developed due to the self weight of the footing is neglected. Okay, so the soil pressure which is developed due to the self weight is neglected in the design of footings. Question number 105. The minimum thickness of footing provided as per IS 456 at edges is 150 mm. So at edges, 150 mm is the minimum thickness of footing that needs to be provided as per IS 456. And in footing thickness, the thickness is decided based on the shear criteria. Okay, so remember, so the thickness is decided based on shear criteria in footings, whereas the reinforcement is based on the bending criteria. Okay, so reinforcement is based on bending criteria, thickness is based on shear criteria in footings. Question number 106. The critical section for bending moment considered for the footing design is A, at face of the column or wall, and B, at section halfway between the face of column and center of column. Okay, so face of the column means if this is a column, so this will be your critical section for the movement. And the another condition is that if this is a column and this is the center of your column, center of the column to the center of column to the facing. So this is your facing, right? And this will be the center of the facing and the column center. Okay, so this will be your critical. Okay, so that is, this is your B and this is your A. Okay, so these are the conditions for the critical section for bending moment. And the critical section for one-way shear. So this one-way shear is also called as punching shear. Considered for footing design is at. So this is at effective depth from face of the column. Effective depth from the face of the column. Okay, so this is for one-way shear. Remember, this is for one-way shear. Okay, and for two-way shear, the critical section will be half of effective depth from the face of the column. So half of effective depth for two-way shear, and effective depth from face of the column is for one-way shear. Question number 108. The bearing stress on the loaded area shall not exceed the permissible bearing stress into under root A1 by A2. Okay, permissible bearing stress into under root A1 by A2. Okay, so this A1 will be the area of footing, and A2 will be the area of bearing, that is your column area. Usually the column area will be taken. Okay, footing and column. Okay. And what is this bearing stress? So this bearing stress is 0.45 FCK if it is in a limit state method, and if it is working stress method, it will be 0.25 of FCK. 0.25 of FCK. Okay, so this is 0.45 FCK and this is 0.25 FCK for limit working stress method and 0.45. So remember this equation. Usually this equation will be asked 0.45 FCK into under root A1 by A2 for bearing stress. Question number 109. The longitudinal bars in column are extended into footing with 90-degree bending with sufficient development length if bearing pressure exceeds the limiting value. If bearing pressure exceeding the limiting value, so you need to extend the longitudinal bars of the column into footing with 90-degree bending, and you have to provide the sufficient development length. Okay, when the bearing pressure is exceeding the limiting value. So that what is the limiting value? So that is 0.45 FCK into under root A1 by A2. Question number 110. As per IS 456, the final deflection of horizontal member from cast level of supports of floor should not exceed span by 250. So the final deflection of a horizontal member should not exceed span by 250. Span by 250. Okay. And also if partitions, so the deflection after partitions and the application of floor finishers. So in that case, the deflection should not exceed span by 350 or 20 mm. Span by 350 or 20 mm. And this span by 350 or 20 mm, this is to prevent the damage for the floor finishes. This is to prevent the damage for the floor finishes and the partition walls. Okay. Question number 111. The most permanent critical deflection in beams is due to shrinkage. So this is all another way you can also call it as differential shrinkage. So because of this shrinkage, you will have the most permanent critical deflections. Permanent deflection means it will be there throughout the life of the member. Question number 112. If web width to flange width ratio increases, then the actual deflection will decreases. Okay. So flange width, if the flange width by if web width by flange width, BW is your web width and BF will be your flange width. Okay. So if web width by flange width is increases, the deflection will decreases. This is vice versa. Vice versa. Okay. Question number 113. The permanent deflection in a RCC member is caused due to creep and shrinkage. Creep and shrinkage. And temporary deflection is due to imposed loads. Question number 114. For structures other than in inaggressive environment, the surface crack width shall not exceed 0.3 mm. 0.3 mm. So for structures other than in inaggressive environment, aggressive environment in the sense like in a marine or in salt water constructions or chemical in a construction in a chemically active area. So those are called aggressive environment. Okay, other than these areas are comes under inaggressive environment. So in inaggressive environment, so the maximum crack width is 0.3 mm. Whereas in aggressive environments, so the crack width shall not exceed 0.004 into nominal cover. So 0.004 into nominal cover. So this should be checked near to the main reinforcement. Okay. So 0.004 into nominal cover in aggressive environment. So other than these areas, in the value is 0.3 mm. Question number 115. The one of the disadvantage of working stress method is, so this working stress method is uneconomical because you'll get a large section areas. Question number 116. The modular ratio in working stress method is given by 230 divided by 3 into sigma CBC. 230 divided by 3 into sigma C, you'll get the modular ratio. Okay. There are another equations also there for modular ratio. That is the modular, usually you will be using this equation, that is modular ratio is equal to Young's modulus of steel divided by Young's modulus of concrete, ES by EC. Okay. And another equations are that modular ratio is equal to stress in steel divided by stress in the bending compression, concrete in bending compression. So the CBC means concrete in bending compression. Okay. And the equivalent area of concrete is equal to M into AST. Try to remember this equation also. Okay. So usually in working stress method, you will be converting the steel into a equivalent area of concrete. So here you will have steel like this, right? So we'll be converting the steel area as a concrete area for design. Okay. So this equivalent area of concrete will be equal to M into AST. Okay. Next. Question number 117. In working stress method, the stress strain variation of concrete and steel are considered as both are linearly elastic. Here both are linearly elastic. Even the stress will be like this, even the strain will also like this. Both are linear. Whereas in limit state method, your stress will be non-linear. So like this in limit state. Whereas in working stress, both concrete and steel are linearly elastic. Remember. Question number 118. The equivalent area of concrete that can replace the area of steel for the analysis in working stress method for M30 concrete and steel of area 1300 mm square. So you know that the equivalent area of concrete can be calculated by multiplying M with AST, modular ratio into area of steel. So area of steel he has given in the question itself, that is 1300 you need to find out the modular ratio. So for modular ratio, what is the formula? It is 230 divided by 3 into sigma CBC. Okay, so you need to know the sigma CBC value. For finding sigma CBC value, simply you can divide the concrete grade with 3. Okay, characteristic value of concrete divided by 3 will give you the approximate value of sigma CBC. Okay, so here what is the sigma CBC? Here the FCK value is 30. So 30 divided by 3 will give, it will be 10, right? So 280 divided by 3 into 10 you will get 9.33. Okay, so this is your M. Okay, so remember the sigma CBC values, you can get this sigma CBC values by dividing concrete by 3. So if you remember, we have discussed the partial safety factors for working stress method also, right? So for working stress method, the partial safety factors are 3 for concrete and steel 1.78. Right? So this 3 is nothing but your partial safety factor. Okay. So therefore, for the equivalent area of concrete will be 9.33 into the area of steel, that is 1300. So it will be 12,129. 12,129 is the correct answer. Question number 119. The moment of resistance of the section in working stress method is given by. Moment of resistance is equal to Q into BD square, Q into BD square, whereas Q is called as moment factor. So Q is given by half of sigma CBC into K into J. Half of sigma CBC into Kj. Okay. So whereas here J is called as lever arm factor. So lever arm factor is nothing but 1 minus K by 3. 1 minus K by 3. So in both the ways you are having K, right? So K is your neutral axis factor. K is your neutral axis factor, and it is given by K is equal to XC, the critical neutral axis, divided by D. XC divided by D. Or you have another equation also for K. K is equal to 1 by 1 plus sigma CBC by M into sigma CBC. Okay. So 1 by 1 plus sigma CBC by sigma CBC. For this, you need to multiply at the denominator. You need to multiply M. Okay. So this is the moment of resistance in working stress method. This is how you will calculate the moment of resistance. Question number 120, the last question. In working stress method, the equivalent area of concrete that can replace the area of steel in compression zone is 1.5 times of M into AST. So initially we have discussed for a singly reinforced section, you will have the steel at the steel only in tension zone. So that will this steel should be replaced with equivalent concrete area by equation M into AST, right? Whereas in doubly reinforced section, the compression reinforcement will be also there. The steel in the compression reinforcement, the steel in the compression zone, and for this compression zone steel, in order to get into equivalent concrete area, it should be multiplied with 1 times of M into AST. Okay. So 1.5 into M into AST is for compression zone steel, and M into AST is for tension zone steel. So remember this. Okay. So these are the important, very most important RCC bits that you may expect in competitive exams, and you can quickly cover this, quickly cover the RCC topics. Okay, and part-1 of RCC most important bits is given in the description. Please go through that video. Okay, and go through the over reinforced section also. So in over reinforced section, you can figure it out whether this is over reinforced or under reinforced. If it is for over reinforced, so the AST will be greater than the AST balance, and XU will be greater than the XU limit or XU balance. Okay. Similarly, the mu will be greater than the mu limit or mu balance. Okay. And over reinforced sections are in over reinforced sections, the concrete reaches first, the concrete fails first, whereas in under reinforced, steel fails first. Okay. And you will have sudden failure in over reinforced, and in under reinforced, you will have a gradual failure. Okay. Thank you all.